Okay, so hello everybody, I'm Ben. I'm a postdoc right now in Adelson Motors Group at Northwestern Physics, and today I'm going to be telling you about the energetic costs and the evolution of cellular signaling. Uh, Sorry, I can't seem to. Okay, so every second of every day, every cell in your body is required to take up external signals in the form of extracellular ligands and pass those signals through the cell membrane down a chain of down a cascade of chemical reactions from the cell membrane to the nucleus where cellular decisions can actually be made. And so each part of this cascade is consistent of a kinase phosphatase push-pull loop seen here in the center. So that kinase phosphatase push-pull loop is essentially an enzymatic loop wherein a kinase population will phosphorylate a substrate, and that phosphorylated substrate can be dephosphorylated by a phosphatase. And so in this signaling scheme, the total information input is the population of input kinase, and the total output is the population of phosphorylated substrate. And since each of these chemical reactions is intrinsically noisy and not completely irreversible, signal errors are propagated and amplified throughout the cascade. And so errors are propagated and amplified. And we can write down a pretty simple model for this system as just a two-state system of X and Y. Again, X is our input and Y is our output. And we can incorporate mass action kinetics to that. And we can go above and beyond this to incorporate things like feedback or time delay in our system as well. But I'm not going to be sharing that with you guys today. So essentially, what we first have to do is figure out what are the enzymatic parameters that parameterize this push-pull loop. And so what we've done is we've scoured the enzymatic databases from PaxDB, SavioRK, and UniProt, and we've come up with distributions for the relevant parameters. So for example, the average population of substrate and phosphatase, the Michaelis-Menten constants for kinase and phosphatase, and the enzymatic constants Kr and ρr, which are the ATP hydrolysis rates in the reaction. And so from these distributions, we can gather all of the relevant parameters except for the reverse hydrolysis rates, K minus R and ρ minus R. And we basically draw thousands of signaling networks from these distributions to test some hypotheses that we have. And so we're interested in essentially microeconomics, meaning that we're interested in the trade-offs between speed, cost, and fidelity in the system. And the two basic quantities that we have to introduce in order to study this are the mutual information between the input and output signals, which we denote I, and the chemical potential, which basically signifies how irreversible the push-pull loop is. And so basically what we do is at a fixed signaling speed. So I should mention that the signaling speed gamma x is the inverse autocorrelation time scale of the input. It's basically the speed at which the input gets turned over. At fixed signaling speed, what we can do is on the left here, we can figure out for a given fixed mutual information, what is the lowest chemical potential that we require to signal with that fidelity? And so basically what we've done in the center is we've plotted that minimal chemical potential for various different signaling speeds. And what we see is that this curve has two main features. The first is that there's a minimal cost below which you can't signal at any speed. And there's a maximal speed limit or bandwidth past which you can't signal at any cost. And so what we see is that the percentage of parameter space that actually allows us to signal with different informations is greatly reduced as we increase the signaling speed. So for example, there's around a 10 to the 3-fold difference between the amount of parameter space required or allowing for signaling with 1 bit versus 2 bits. And so basically what we do is we draw thousands of times from these distributions, and in green we show the minimal cost, the cost at the slow finite speed, and in blue we show the maximal cost at the bandwidth. And so what we see basically is that all of these push-pull loops push up against the physiological range of delta mu. And what that basically signals to us is that these push-pull loops were designed in order to signal robustly at any speed. And again, we see that the percentage of parameter points that allow for this robust signaling is greatly diminished as we increase the information content. Also, what we see is that we can come up with a bound on, or a relation rather, for the bandwidth in terms of our effective gain parameter R naught and the mutual information. And particularly what we see for yeast signaling under osmotic shock is that signaling is essentially optimized. So yeast is doing a very good job of signaling at fast speeds with low chemical potential. And finally, we are interested in looking at the evolutionary pressure to signal optimally. And so people often cite that, lower energy expenditure will provide an evolutionary gain to a system in order to, for example, signal optimally. But if you don't calculate a selection coefficient, then those are essentially empty words. So what we do is we calculate the effective selection coefficient seen in the top right there as the excess metabolic cost, delta C, over the total resting metabolic cost. And we can quantify that excess metabolic cost in terms of the ATP consumption rate of our push-pull loop. And so again, we see that there's a bound there. There's a minimum ATP consumption rate to signal at a given fidelity, at a given speed. And when we actually calculate our selection coefficients, we see that the higher the speed, the larger the selection coefficient. So the larger the evolutionary gains in order to signal with that speed. And so importantly, there's a concept of drift threshold, which is the inverse effective population size. And as long as your selection coefficient is larger than that drift threshold, then selection will take over from genetic drift, and you'll actually be pushed towards fixation of that population with that feature. And so we see, for example, that yeast under osmotic shock signaling, again, is able to signal with selection coefficients that range from, let's say, 10 to the minus 8 to 10 to the minus 3. And that, in general, goes above and beyond the drift threshold. So we're able to say that yeast may be under evolutionary pressure to actually optimize the energetic costs associated with this enzymatic loop. And with that, I'd be happy to take questions, and I'd like to thank my collaborators at CASE for writing the paper and my current advisor, Allison Motter, for providing support.